Hey, Mr. Qualls, and I'm going to make another video, a little more technical than the last one. You know how I had my string on the last one, and we were talking about how the rope stretchers or the surveyors in Egypt would use this, and they would make a right triangle on the ground, and then they would mark where they were, and then they would move, this down this way, have another right triangle, and mark that where that one was, and then they would flip this kind of thing to make another right triangle, and then they would put the right triangle up here, and then they would flip it, and then they would move their way across the floor of the Nile Valley after the Nile had pushed. Well, this is going to be a little more technical on this. This is going to be a proof of the Pythagorean theorem. Now, a proof is something that we don't have a lot of experience with, but eventually, when you study mathematics long enough, proofs become things that you can use as tools later, because once you kind of prove something is true, you don't have to do it again. You can use that idea as, well, if this is true and it's true in every case that looks like this, then we can use that to solve other problems, and we can just move along. It's like it works like part of the rule book or a law of math. And so what we're going to look at here is the idea that, well, what if this a squared plus b squared equals c squared is always true? What can we use that now, instead of having to show, nobody's going to walk up and say, well, what are you doing? Well, how can you just use that? Well, it's a theorem. It's something that has been proven to be true every time, with certain cases, as long as certain rules are followed, that it's true all the time, and we can use it to solve other problems. And then the other mathematicians and scientists and people that know what you're talking about aren't going to ask you to make your argument like, oh, how'd you figure that out? Well, if it's the Pythagorean theorem, they're all going to know it, and then they're all going to realize, hey, this person knows what they're doing too. And this is one of the big tools that we do that with, is the Pythagorean theorem. And so what a proof does is uses mathematical arguments that cannot be denied and are also true. And as long as we stick with true things and we make logical and true statements and arguments through the discussion of what we're doing, if we don't break any rules and we make it all the way through the thing and it works every time, it can become something that we use as just like, hey, everybody knows about this. This is a basic rule, right? And so that's what proofs are all about, is just using something, making an argument that can't be argued against. So if I look at this, this is a square, all right? Square, everything's equal length on the four sides, four right angles. What I'm going to do is I have moved out a certain distance here from this corner, and I'm going to call that length A. Okay. I also came down this length A, and I also moved over this way A, and I moved up this way A distance. Now, if this side, all of these sides are the same length, and I came out the same distance A from each corner, these are all the same distance, same lengths to those dots, and whatever was left is also the same, and I'm going to call that B. Call this B, I'm going to call this B, and I'm going to call this B. I'm going to complete drawing these lines here, and you're probably going to notice when I get done with this, drawing these four lines, I have another square. I have another square inside. So all of these are right angles. And inside here, this is another square. Okay? So what we're going to do is we're going to look at this idea, and we're going to look at it in two different ways, knowing what the area of the entire square is. And I'm going to look at it as, what if I found the area of the entire square by taking this length times this length and found the area of the entire square, or if I looked at the area of this triangle plus this triangle plus this triangle plus this triangle, and then found the area of this square, adding it to those 4 triangles, I will also have the area of the entire square, right? So let's call this C. So we have A, B, and C, kind of like in our last video. This is going to be a standard idea. So when we're talking about the Pythagorean theorem, almost everybody uses A, B, and C when we're talking about this stuff. And this is just one proof. It's one of the easiest that I remember. There are hundreds of proofs of the Pythagorean theorem. And like I said before, once you prove a theorem once and everybody's like, oh, we can use it. Well, everybody's come up. I think there's a president even, I think, that came up with his own proof of the Pythagorean theorem. I don't remember. It might have been, well, the Grover Cleveland comes to mind, but I don't know if that was exactly who. I can't remember off the top of my head who did it. But there are many, many ways to prove this. This is just one of them. It's one of the easiest ways to look at. And so if I want to equate the area of this square and look at it 2 different ways, the big blue square, and look at it in 2 different ways, what I'm going to do is I'm going to look at the area, this length times this length. Now, if we want to look at how long the square is, this length over here would be A plus B. It would be this length plus this length. So if I wanted to have this length times this length, let's use the one on the top because it'll be easier to see that A plus B and then B plus A, well, is that the same thing? Yeah, but this looks like A plus B and this looks like A plus B. So let's do that, okay? So A plus B times A plus B is going to be the area of this square, all right? Now, this is not something that you guys have seen yet, but I'm going to show you. If this was just B out here, and I would distribute the B with the A and the B with the B, it would be B times A, which would be AB, and B times B, which would be squared. And now I have to go with the A and the, and so there's going to be a piece here where you have to kind of trust me that, look, he's not breaking any rules. But all this really is a distribution of B over these 2 and a distribution of A over these 2. And then you just have to keep track of everything down here. Now, the other way that we could look at the area of this triangle, of this big blue square, is if we looked at the area of the triangle here, which is, so I'm going to do that right down here. This triangle would be, the area of a triangle is 1/2 base times the height. Now this is a different B, but anyway, it doesn't matter. They're just variables, so I'm just going to put in where I need to. So the area equals 1/2 base, let's just go with the A, times the height, which is B. So it's 1/2 AB. 1/2 A times B. Now, I don't know what the lengths are, but I do know if I took A times B and I multiplied it by half, I would get the area of that triangle. Well, there's not just one of those triangles. There's one up there, there's one over here, and there's one here. So there are 1, 2, 3, 4 of these triangles. So really, what we're looking at, if we want all 4 of those triangles, we need to have 4 times 1/2 AB. And 4 times 1/2 is 2. So this becomes 2AB. So this right here represents the area of all 4 of these triangles put together, right? So now I have 2AB. So I'm going to put 2AB over here. I'm going to put 2AB right here. And I'm going to add that to, what else do I have? Well, I have these triangles now. And now I need the area of this square inside. Well, the area of a square is side times side, or length times length, or C times C, or C squared. So if I wanted to have the area of that triangle, it is C times C, or C squared. So, or excuse me, did I say triangle? The area of this square. So the area of this square plus the area of these 4 triangles makes the entire blue square. This is C squared, and these 4 are 2AB. Now, when I look at this thing, and I multiply A plus B times A plus B, what I have to do is I have to make sure that I distribute. If it was just B times A and B times B, I would distribute the B over the A and the B. So B times A would be BA, or I could write it down AB, which I will, AB, plus B times B is B squared. Then I've taken care of the distribution of this one over these two, but now I need to go back and make sure that I use the distribution of this to the A and this to the B, all right? This is something that you're gonna do in algebra later. It's multiplication of binomials, and this is really a binomial squared, so it's a special situation. It's also, we use this thing called FOIL, F-O-I-L, which helps you keep track of everything. And A times B is AB. And then A times A is A squared. And we're going to add all of this together. And we have A squared plus AB plus AB. That's 1AB plus 1AB. So it's 2AB. And this is B squared. So what does this give me? Well, this is the length of this side, and this is the length of that side. And that times that, which is this, this is the area of the entire square. So I'm going to put A squared plus 2AB plus B squared as the area of this for the square, the big square. So it's A squared plus 2AB plus B squared equals C squared plus 2AB. Now, what we want to do is we want to look, this is equal to this. And if you had something that said, that had something on both sides of the equation that didn't need to be there, you could simplify the problem by either adding, subtracting, multiplying, or dividing both sides of the same thing and simplify your problem. Well, can we simplify this equation? This is an equation. This quantity and this quantity are both the same area. And if we can simplify it, we should, because that's what mathematicians do. So I have a 2AB on this side, and I have a 2AB on the other side. So I'm going to subtract 2AB and 2AB. Now, 2AB minus 2AB, that's a 0 pair. All I have on the other side is C squared. Same thing happens over here. 2AB minus 2AB, that is also a 0 pair. And what that's going to do is it is going to remove the complications from both sides. We are simplifying both sides. And when we do this, all we're left with is A squared and B squared. This is a proof of the Pythagorean theorem. What we did was we compared the overall area to the area, if we took it by pieces, equated them to each other, made an equation, and then simplified the equation, and we came up with the Pythagorean theorem. Now, did I put any numbers or any values in here? I didn't put any numbers. I didn't say that A had to be 5. I didn't say that B had to be 20. I didn't say that C had to be anything. I didn't identify any numbers up there. I didn't give any quantities. Therefore, we can make the argument that it does not matter what numbers we put in here. This is going to work. All right? This is going to work. Now, sometimes it's not going to be very pretty. Sometimes it's going to be pretty ugly because there are going to be decimals involved. All right. So for instance, if we had 3 squared plus 4 squared equals 5 squared, this is true. 9 plus 16 equals 25. Right triangle. So if we had a right triangle that had a 3 and a 4, I know that this side has to be 5 every single time. If I have a triangle and it's a 3, 4, 5 triangle, it's a right triangle. The 5 is the hypotenuse because it's got to be the longest side. It's across from the right angle, and the 3 and the 4 are the legs every single time. If I multiply both sides of this equation by 2, and I have 2a squared, 2b squared, 2c squared, this becomes 2 times this, 2 times this, and 2 times this. And all it does is it doubles everything. It's also true. If I had a 6 here, and an 8 here, and a 10 here, 6 squared plus 8 squared plus 10 squared. 6 squared is 36, plus 8 squared is 64. 10 squared is 100. 36 plus 64 is 100 equals 100. This is also a right triangle. So there are a number of triangles, and actually there's an infinite number of triangles that all fit these patterns. But there are a number of patterns that if you know 3, 4, 5, well, 6, 8, 10 is just 2 times 3, 2 times 4, and 2 times 5. So 30, 40, 50 is 10 times 3, 4, and 5. 30, 40, 50 is going to be a right triangle. 300, 400, 500 is going to be a right triangle because it's just a scaled up version of this. Not all of them work this way, however. If we were to take a squared plus b squared plus c squared, and we were to say that I have a right triangle, and said that this right triangle here has a 3 up here and a 7 down here, and I wanted to know what that is, this is now c. Well, a squared would be 3 squared, b squared would be 7 squared, and then we've got c squared over here. Well, 3 squared is 9, 7 squared is 49, 49 plus 9, it's going to be c squared. 49 plus 9 is 58, is c squared. Now, 58 is not a perfect square. It's not a number. When we find the square root of it, we get an integer. The ones that we were dealing with before, the 3, 4, 5, were. This one is not. So 58 is a number that we need to find the square root of this number in order to figure out how long this line is. And the perfect squares that surround 58 are 49 and 64. So 7 times 7 is 49, 8 times 8 is 64. So 58 sits somewhere between there. So we're going to have to estimate what this might be. And we know that side's got to be longer than 7 because it's the hypotenuse, and this is 7. But we're either going to use a calculator or we're going to estimate our square root. But that is part of the next lesson. Okay, how do we do this if everything isn't a whole number? Or an integer, excuse me. Well, I should just say whole number, right? If it's an integer, that's okay. But what if I got a -5 for this side? That's not going to work either because you can't have a negative length for a side of a triangle. Okay, so next video is the performance part. So I'm going to take some time, make that. It'll have graph paper, you'll need some scissors, things like that. And then we'll get on with the study of the Pythagorean theorem. Thanks for watching this proof.